Assalamualaikum and hi. My name is Syafiq bin Iskandar Nasruddin, and I want to present about my final year project, which is performance analysis of water cooled chiller at engineering complex. Okay, my supervisor is Puan Binti Bahsan, and my co-supervisor is IR Haji Anuar bin Hashim. For the panel 1 is Dr. Muhad Rozi bin Nawi, and the panel 2 is Sir Mohamad Mazwan bin Mahat. Okay, for the introduction, since Malaysia is located in Southeast Asia, it is known to have tropical weather, which average temperature is 32 degrees Celsius, where air conditioning within a building is important. To accomplish an optimal temperature satisfaction, chiller is the best mechanism in achieving the desired result. Chiller can be divided by two types, which are water-cooled chiller and air-cooled chiller. Both water-cooled chiller and air-cooled chiller has common components, which are condenser, evaporator, compressor, and expansion device. An analysis should be executed to obtain the knowledge of the plant. When selecting a chiller, the efficiency and coefficient of performance in rated operation or partial load are important elements. Therefore, the purpose of this research study are to analyze the current of performance of water-cooled chiller system using energy analysis and compare it with the test data from manufacturer. The project will be analyze the performance of water-cooled chiller based on the coefficient of performance and load factor. This is the diagram of water-cooled chiller, where the evaporator and compressor are in the chiller pipe, and have cooling tower, condenser water pump, and chill water pump, and air handling unit or FCU fan coil unit. For the problem statement, district cooling system with thermal energy storage was used in engineering complex. TES was operated during the night to produce ice water and stored in the ice cells. However, the TES has been replaced with current water-cooled chiller due to leak on ice cell and drop the system performance. Even though the cost of electricity when using TES is lower than water-cooled chiller due to runs during night, but it requires high maintenance costs and difficult to do maintenance when leaking occur. Objective: to analyze the current performance of water-cooled chiller system using energy analysis, to compare the current performance with the test data from manufacturer, to investigate the effects of various operating conditions on the performance of the water-cooled chiller system. Scope of work: focus on the individual component such as evaporator, condenser, and chiller in water-cooled chiller system, which will be analyzed by using energy analysis. The project will be analyze the performance of water-cooled chiller based on the coefficient of performance (COP) and load factor (LF). The analysis will cover daily sets of the actual data from water-cooled chiller system from 5 April 2021 to 9 April 2021. An Excel program will be developed to investigate the effects of various operating conditions such as condenser, inlet temperature, chill water inlet temperature, and load factor on the water-cooled chiller system. Limitation: students were allowed to enter UiTM, but only for a short time period due to Movement Control Order (MCO) COVID-19. The operation data only can be collected for a week due to pandemic of COVID-19. The chiller was not on stable condition due to leaking at underground pipe. The water-cooled chiller was not fully operated on its usual operating states. The chiller was shut down on all trips during collecting the due to low water incoming at condenser. This is the methodology. From For this presentation, I will explain from the preliminary study, visit and pre-data collection at chiller plant, collect actual data, data analysis, observe and compare the result with discussion, and about the total in the report writing. First methodology is studying the plant operation of water-cooled chiller system. In engineering complex at UiTM Shah Alam, there are 4 chillers of water-cooled chiller type that will be supplied for 8 buildings, which are Block 1 to Block 5, Tower 1, Tower 2, and Podium. Each chiller consists of 900 refrigerant ton capacity and using R134A as a refrigerant. Figure show the flow process of water-cooled chiller at the engineering complex. The cool water from chiller will be supplied to chiller water pump CHWP and will go to the heat exchanger hex before supply to the building. The hot water that return from the building will back to the chiller and go to condenser pump to elevate the water to the cooling tower. Cooling tower will reduce the temperature of water by remove the heat before return into the chiller. This is the image of water cool chiller of the chiller at the chiller plant. Data collection at chiller plant. The water cool chiller has been installed at engineering complex and the manufacturer specification is shown in the table 1 below. The data related to the performance was recorded by a building automation system and was analyzed in the Excel spreadsheet. This is the chiller data overview. Collecting actual data and Excel spreadsheet preparation. The water cool chiller has been equipped with building automation system, BUS. It is easy to monitor and control the chiller during operation. The building automation system enables facility managers to monitor, track and respond to the performance of facility assets. By using BUS system, the data can be recorded and Excel spreadsheet was used to calculate and tabulate the difference of COP, load factor, efficiency of the water cool chiller. From April 5, 2021 to April 9, 2021, data related to each component of the water cool chiller, such as mass flow, temperature, COP, and efficiency, were collected from the engineering complex plan for a period of 5 days. The data was taken 4 times a day from 10 a.m. until 4 p.m. The data was monitored from the BUS system and in the control room at 10 a.m., 12 p.m., 2 p.m., and 4 p.m. And for information, the chiller plant start to run at 9 a.m. and will turn off at 5 p.m. This is the image when I'm collecting the data from the digital panel at the chiller, and this one is from the BUS system. We need to use the UATM server to log in the BUS system. This is the example of the BUS system, and this is the table that made by using Excel spreadsheet to collect and record the data, which we have evaporator, chiller water pump, condenser water pump, and power. This is the overall chiller. We have cooling capacity, chiller input, chiller efficiency, and chiller COP. As I said, this is for the overall. This is for 6 and 7 April, 8 April, and 9 April. This is the result and data analysis, which I have been calculated for COP, load factor, efficiency, heat removed by condenser, and heat removed by the chiller. Okay, for the cooling capacity. Cooling capacity for the system is fluctuated, with the highest is 3,392.7 refrigerant ton at 10 a.m. on Friday, while the lowest is 1,700.2 at 2 p.m. on Wednesday. This one. The lowest value on Wednesday was due to chiller 3 and 4 were tripped because of the low water flow in condenser, and as shown in the chart from 2 p.m. until 4 p.m. the value was lowest. However, the stable and good cooling capacity can be seen on Thursday, the yellow one, because the chillers were running all the day, while on other days some of the chillers were shut down or trip occurred. For coefficient of performance of system, when COP is lower, it indicates the higher power consumption of chiller, lower efficiency, and higher operating costs. The COP of system fluctuates. The highest value was recorded on chiller 3 on Wednesday, and the lowest COP value was recorded on chiller 1 on Tuesday, which were 3.81 and 0.49. The higher value of COP on Wednesday was occurred at 10 a.m. where the chiller was start to run that need higher cooling capacity, thereby increasing the performance. Meanwhile, the lowest value of COP on Tuesday due to chiller 1, which was not running on 10 a.m. in the morning. For the hourly COP, the Thursday data was selected to standardize the data from cooling capacity section, and due to stable variation of COP, the COP value is in the range of 1.68 until 0.266. The highest COP is recorded at 10 a.m., which is 1.68, and the lowest COP is recorded at 10 a.m., which is 0.266. This can be explained by the reduced cooling requirement from working hours that require high cooling capacity. The reduction in cooling requirement reduces the energy flow in evaporator, thereby reducing the performance of system. Chiller 2 was selected as the good and stable variation of COP value. The COP value is in the range of 1.15, 1.15 to 1.49. The highest COP is recorded at 2 p.m., which is 1.49, and the lowest COP is recorded at 10 a.m., which is 1.15. However, the chiller system needs an improvement based on ASHRAE's COP classification. Good piping and pumping system can increase the system performance and reduce the losses. The lowest load factor indicates that load is using the electric system less efficiently. Thus, the higher load factor is the better. However, load factor is always less than 1. The load factor of the system will fluctuate. The highest value of recorded on chiller 2 on Wednesday, and the lowest load factor value was recorded on chiller 3 on Wednesday, which were 0.828 and 0.249. The constancy of the load factor on Wednesday was due to chiller 3 and chiller 4 were automatically cut off trip by safety device in the chiller system at 2 p.m. and 4 p.m. during the operation because there was no water flow in condenser. For the hourly load factor, the Thursday was selected due to stable variation of load factor and to standardize data obtained from previous COP and cooling capacity. The load factor value for a whole day can be seen in the figure. As can be seen, chiller 2, the red one, shows stable value of load factor compared to other chillers. Thus is the chiller 2 load factor. The chiller 2 was selected due to more stable compared to the other chillers. The load factor value is in the range of 0.7 to 0.88, where the highest load factor is recorded at 2 p.m., which is 0.885, and the lowest load factor is recorded at 12 p.m., which is 0.701. The trend of load factor throughout the day is similar to the trend of COP. The load factor is also related to the energy flow in the evaporator and system performance. Heat rejected from condenser and chiller. Heat rejection is the energy removed from the refrigerant during the condensation process. Normally, the heat dissipation is 50% to 25% greater than the cooling effect in the evaporator. As can be seen in the chart, the red one is the heat rejected from condenser, and the blue one is the heat rejected from chiller. For the hourly heat rejected, the Thursday data was selected due to stable variation of data and to standardize data obtained from previous COP, load factor, and cooling capacity. The highest rejected in condenser was 3181.93 kW, while in the chiller was 2553.89 kW. Both of the highest data was occurred in the morning where the chiller started to run. The trend was decreasing throughout the day. Daily efficiency of water-cooled chiller. The average efficiency of the system can be seen through the bar chart. The highest value was recorded on chiller 3 on Thursday, and the lowest value was recorded on chiller 3 on Wednesday, which were 1.52 kW per ton refrigerant and 0.19 kW per ton refrigerant. And the lower the kilowatt per ton refrigerant, the more efficient of the system. Figure above show the average COP of testing report from manufacturer against the COP analysis for Chile 2 that has been calculated in this study. The COP from manufacturer were highest than COP analysis. By this comparison, it states that the chiller at engineering complex plant can improve more further. The manufacturer chiller was running at 25% of load during the morning and had full load at 2 p.m. As can be seen in the chart, as can be seen in the bar chart, at the 10 a.m. the chiller only running 25% of load, while for 2 p.m. the chiller running at 100% of load. However, from the analysis that we get from our chiller plant, we only get this number 1.15 and 1.49. By solving the leaking at underground pipe, use the suitable size of pipe and high power of pump, the water losses can be solved and increase the COP of the chiller. So for the conclusion, the research study at the water-cooled chiller plant at engineering complex in Shah Alam has come to a conclusion. In this study, the new installed water-cooled chiller has been selected as main of analysis. This study was conducted to calculate the coefficient of COP, load factor, heat rejected, and efficiency of the chiller system. The average COP is in the range of 0.49 to 3.81, where the higher value of COP on Wednesday was occurred at 10 a.m., where the chiller was start to run that need higher cooling capacity. Meanwhile, the lowest value of COP on Tuesday due to chiller 1 was not running on morning on 10 a.m. in the morning. Hence, the average of COP of chiller 1 was lowest compared to others. However, during the data were collected, there were many hindrances such as the chiller was not running consistently, thus it affected the data of the others chiller. During the data taken, the chiller was not run at full load due to underground pipe leaking. In order to improve and maintain the chiller plant, the competent person in HVAC field need to monitor the chiller. The piping and pump system need to be checked regularly in order the system can reduce the losses and give better performance. And that's all for me. Thank you. And if you have any question, you can contact my number 013-3389-260 or my email syafiqshami@gmail.com. Thank you for watching and for listening.